Our next speaker is Anna Franckowiak, and she will talk about the experimental overview in astroparticle and cosmology. Very good. Thank you. 30 minutes.
Thank you. Thanks for having me. After seeing Tim in his big sweater, I conclude that the weather in Stockholm is much worse than it's here in Germany. But after his excellent talk, giving an overview of dark matter, I will now switch gears a bit and focus more on astrophysics, especially on multi-messenger astronomy. So multi-messenger astronomy can be compared to this picture of an elephant with blind men touching the elephant from different positions. And each of them will get a very different view of this animal that they are touching. And I think the same is true for the different messengers in the universe. Every time we add a new wavelength, we see the universe from a different perspective and we can learn something new. And that's even more true for different messengers on top of electromagnetic radiation that we use classically to do astronomy. So the new messengers that we're looking at are cosmic rays, neutrinos, and gravitational waves. So my talk will mostly focus on the neutrino part here. But as you know, there is a very tight connection between cosmic rays and neutrinos. Therefore, I will briefly talk about cosmic rays as well. So cosmic rays bombard us all the time from all directions, and they are mainly protons or heavier nuclei, and they can be detected by measuring the extended air showers that they produce when they collide with the molecules in the atmosphere. And that can be done by water-Cherenkov detectors on the ground, or also with fluorescence telescopes measuring the fluorescence light in the atmosphere produced by the shower, or a combination of the two. So what have we learned from those measurements using extended air showers is that those cosmic rays reach incredible high energies, larger than 10 to the 20 electron volts, and that's 10 million times more than what we can put in a single proton with the Large Hadron Collider. So the question here is now what are those powerful accelerators in the universe that are able to accelerate particles to those incredible high energies? The problem now, if we directly observe the cosmic rays, is that they are charged particles. So on their way from the source to us, they will be deflected by magnetic fields. So once we measure them on Earth, they usually don't point back to their origin anymore. And this is now where this multi-messenger approach is very useful, because photons and neutrinos are produced in interactions of cosmic rays with ambient matter or photon fields. So yeah, you can either have proton-proton interactions or proton-photon interactions, and in both cases you produce pions, either neutral pions that would then decay to gamma rays, or if you have charged pions here, you produce 3 neutrinos in the decay chain. And now those are neutral particles, so they point back to the source and can help us to find the origin of the high energy cosmic rays. So the problem with gamma rays usually is that they are not exclusively produced in those interactions with of high energy cosmic rays, but they can also be produced by leptons or electrons. So it's usually very hard to disentangle. However, there's a few cases where it was actually possible to really use gamma rays to point to proton acceleration. And I show an example here, this supernova remnant IC443, where the so-called pion bump signature was detected in the spectrum. So you see the gamma ray spectrum here, measured by the Fermi Large Area Gamma Ray Space Telescope. And what you see here is that you can model this with a leptonic or a hadronic model, and you clearly see this pion bump signature at low energies, which is really a smoking gun signature for hadronic production of the gamma rays. However, this pion signature only showed up in a handful of supernova remnants in our galaxy. And the problem here is that you see that the energy decays quickly. So those sources do not reach PeV energies. And this is what we see in the cosmic rays, that the galactic cosmic rays reach really high energies. So those sources are probably not the pevatrons that we expect somewhere in the galaxy. However, it's a first indication that supernova remnants are able to accelerate cosmic rays. So there is some indication for a pevatron in the galactic center, and this was found in a measurement by the Hess ground-based Cherenkov telescope that measures gamma rays even at higher energies. And they managed to detect the diffuse gamma ray emission in the galactic plane around the galactic center. And in this plot, you see that this gamma ray emission is spatially correlated with gamma rays with the molecular gas in the galactic plane that you see in this with this white contour shown here. So that's already an indication that that this gamma ray emission is of hadronic origin, because you would have proton-proton interactions with this molecular gas, and then pion decay producing the gamma rays. And on top of this, the energy spectrum shown in red here of the diffuse emission now extends really to high energies, and you can only explain this if there are PeV protons present in the source that would then extend the gamma ray emission to those high energies. So this is the first indication that the galactic center is actually a pevatron. And it also tells us that there was some past activity of the supermassive black hole in the Milky Way. So recently now we have two new detectors that measure gamma rays at even higher energies, above 100 TeV. And those are also ground-based particle detector arrays. And what was really the game changer here is that they also use muon detectors buried under the ground that allows them now to distinguish the gamma ray showers from proton showers that is like a huge background that they have to deal with. But thanks to those muon detectors, they can actually do it. And for the first time, they actually find PeV photons from the galactic plane. And the sky map is shown here, and you see all the this blue circles here show like single PeV photons coming from the galactic plane. So this really now confirms the existence of pevatrons in the galactic plane. However, it's still an open question if those PeV photons are produced in leptonic or hadronic processes. So how could we really now answer the question, what are the hadronic accelerators in the sky? And really the smoking gun signature for this hadronic processes would be high energy neutrinos. So currently we have 3 operating detectors. Is the ice cube detector at the South Pole. That is 1 cubic kilometer of ice instrumented with sensitive light sensors to detect the secondary charged particles of the neutrino interaction, and also reconstruct the direction and the energy. And similar but smaller detectors are operated in the Mediterranean and in Lake Baikal. And in both locations, there are cubic kilometer detectors currently under construction. And also at the South Pole, there are plans to build an even 10 times bigger detector. So can we detect neutrinos from the galaxy? We have detected a diffuse neutrino flux that is shown here, and the 2 different colors just indicate the different detection channels used here. But this is now the diffuse flux seen from everywhere in the sky, and the question is how much of this could be accounted from galactic sources. And to answer this question, a template analysis was done. So by modeling the cosmic rays and how they propagate and interact in the galaxy, you can produce gamma ray and neutrino emission maps of the sky. And those models can be constrained by the existing gamma ray data and also cosmic ray measurements. And from that, you get then a neutrino flux prediction. And this template now can be used to look for neutrinos only from that direction. And that has been done, and no significant excess of neutrinos was found, unfortunately, from the galactic plane yet. But here again, you see the diffuse flux here. And in gray here, that's the prediction from this galactic propagation code of the neutrino flux you would expect from the galactic plane. And overlaid, you see the upper limits that are the result of this analysis. In blue, for example, you see that with the upper limits, we are now at the point where we're basically touching the prediction, but we cannot, we haven't detected anything, but we can also not rule out anything at this point. But this analysis tells us that the contribution of the galactic neutrino flux to the diffuse neutrino emission is less than 8.5%. So really, most of the emission we are dealing with in this diffuse neutrino flux has to be of extragalactic origin. So yeah, what could be the sources of those neutrinos? In this plot, now the neutrino flux is brought into perspective with the diffuse gamma ray flux shown in blue and the high energy cosmic ray flux measured by Auger shown in green. And you see that they're more or less all on the same level, and that tells us that similar energies are injected into gamma rays, neutrinos, and cosmic rays, which is interesting and maybe tells us that those fluxes are somehow connected. Now at this point, we don't know where the neutrinos come from, we don't know where the cosmic rays come from, but we know pretty well where the gamma rays are produced. They are mainly produced by blazars, and blazars are active galaxies, so supermassive black holes in the center of a galaxy that actively accrete and shoot out a jet. And if we look into that jet, then we call this a blazar. And those dominate the gamma ray sky. Now we can check if gamma ray detected active galaxy also dominates the high energy cosmic ray sky, and the Auger collaboration has done a study where they look at anisotropies in the sky, and now they look only at the highest energy. So earlier I told you that the cosmic rays wouldn't point back to their source because they get deflected, but at the highest energy, actually this deflection is, well, it's still there, but it's not as big. And you can still try to do some correlation studies with close by sources. And this was done here, and they used different model classes to look at, for example, this gamma ray AGNs and also starburst galaxies. And what they found is that actually the starburst model fits best and fits better than the assumption of an isotropic distribution of the arrival direction of the cosmic rays at 4 sigma level. And for comparison, the gamma ray AGN only reached a 2.7 sigma level. So the starburst model is preferred here. And what you see here is this is the observed sky map, and that can now be compared to a model sky map based on this assumption of a certain source catalog that's shown here, and then you get the residuals here. So really it looks like it's really matching, it's matching pretty well. But also the gamma ray AGNs still have a reasonable match at this point. And here keep in mind that really this only works for close by sources, because the highest energy cosmic rays, they would interact with the cosmic ray microwave background, and they can only reach us from the local universe. But it's an interesting indication that starburst galaxies could produce those high energy cosmic rays. But if we really want to look now at the whole universe and not only focus on the local universe, then we cannot do this directly with cosmic rays, but we can try to do this with neutrinos. So where do the neutrinos come from? That we measure in this diffuse neutrino flux. To figure this out, we can look at a sky map of neutrinos, and this is shown here. a 10-year sky map from IceCube and an 11-year sky map from Antares, and you don't really see the individual events in this map, but you see the p-value. The p-value basically tells you how large an excess you would find, or how likely an excess that you find is compatible with background. So you want a really small p-value to have a significant excess, or in this case, a large minus log 10 p-value in this representation. So now we can look at the hottest spots found in the sky and look at the local p-values at that position. And IceCube finds a value of 3.5 times 10 to the minus 7. Also, Antares has a small p-value of 10 to the minus 6. But now you have to take into account that you haven't only looked at this one position, but you basically looked at all the positions in the sky. That gives you a huge look elsewhere effect, and you have to correct the local p-value with the trials factor accounting for all the positions that have been looked at. And then you get the post-trial p-value, and then you see here that what you end up with is not significant anymore. So what is really key is how many places in the sky you have looked at. So if you already know where to look, you can reduce this trial factor. So one can make an educated guess and look only at a list of sources, and this was done. So 110 sources have been predefined as potentially interesting neutrino emitters based on their gamma ray properties. And then instead of looking at the whole sky, now only the analysis has only been performed at those 110 positions. And the most significant source of this 110 sources was NGC 1068. And because the number of trials is now much smaller, we find a significance of almost 3 sigma. And interestingly, the source actually lines up with the hottest spot found in the all sky analysis in the northern sky. But now just the trial correction is a different one, and actually gives us a more significant result. So what is this source, NGC 1068? It's also known as M77, and it's one of the closest Cypher 2 galaxies. Now, Cypher 2 galaxy is also an active galaxy, but for the blazars, you look into the jet, and in this case, now you look from the side to the source. And this source has AGN activity, and it also has star forming activity. So there is potentially 2 processes that could produce high energy neutrinos. So this is actually very interesting. And what was found in this analysis is that the neutrino spectrum actually is quite soft. And now we go back to the multi-messenger approach. We now compare the neutrino spectrum to the gamma rays emitted by this source. So in green, you see the neutrinos, and in red, you see gamma rays measured by Fermi. And at highest energies, there's the data from ground-based Cherenkov telescopes that measure TeV gamma rays, and you see that those are only upper limits. So there are no gamma rays detected in the energy range where we see the neutrinos. And that's actually quite interesting, because at the production at the source, you would expect that you produce gamma rays at a similar level where you also produce the neutrinos. So those gamma rays, somehow something has to happen to the gamma rays if we believe in this association. They have to be absorbed somehow. So there has to be some very dense photon fields in the source that could absorb the gamma rays. And that's a bit tricky, because those very dense photon environments are usually hostile for proton acceleration. But it could be that you produce the neutrinos and the gamma rays in one place, and then there is another place where you absorb the gamma rays. So really combining the neutrino and gamma information now tells us something about the environment in the source. So there's another approach how we can find the sources of the high energy neutrinos, and that's by using a target of opportunity program. And the idea here is that we detect high energy neutrinos in real time, for example, by IceCube, but also the other neutrino detectors have a similar program. So we would detect the neutrinos, measure their direction and energy within a few seconds. And then for the most interesting events where we are quite sure that they are of astrophysical origin, we would send out an alert to the community of astronomers, and everyone who has a telescope could then point into the direction where the neutrino comes from and hopefully find an electromagnetic counterpart to the high energy neutrino that would then allow us to identify the source. And this increases our sensitivity, especially to transient or variable sources, right? Because if you don't look fast enough with your telescope in a real-time program, you might miss a rapidly fading afterglow or electromagnetic signature in that direction. So in this program, two interesting sources have been identified, and I briefly want to go through those two sources. So the first was a gamma ray blazar called TXS 0506. And again, a blazar is an active galaxy where we look right into the jet. And the second source is a so-called tidal disruption event called AT2019 DSG. And what happens in case of a tidal disruption event is that you have a quiet supermassive black hole in the center of a galaxy, and a star is approaching too close, it would get like ripped apart by the tidal forces, and some of the debris from the star would get accreted onto the black hole, and in some rare cases you could also produce relativistic jets in this accretion process. And they are kind of a new source class, because only now, due to new optical surveys, we really detect a lot of those sources. So we have maybe around 50 sources detected so far, while like blazars we know about like 1,000 of them. But there was like already models that predict neutrino emission from tidal disruption events. So let's talk about the blazar detection first. So a high energy neutrino was sent out by IceCube, and in that direction, the Fermi gamma ray telescope found an already known gamma ray source, Texas 0506. And in addition to the spatial coincidence, this source was also flaring at the time where the neutrino arrived. And you see this here in the light curve. So you see the gamma ray flux in days relative to the arrival of the high energy neutrino. So you see that with Fermi, we already cover almost 10 years of data. And there was some flaring activity in the past, but really the largest flare was detected at the arrival time of the neutrino. And on top of this source in this follow-up program after the neutrino arrived was also for the first time detected in TeV gamma rays by the MAGIC ground-based Franckowiak telescope, and you see this on the right here. So this is the 50% and 90% neutrino error circle, and you see that the source is really right in the center. And those high energy gamma rays actually tell us that the source is likely to produce also high energy neutrinos. So this has a chance coincidence of 0.1%, so it's also at 3 sigma level. Maybe as particle physicists, you're not excited about this, but this was really the first and only 3 sigma association for high energy neutrinos that we had at this point. And if we believe this connection, then it tells us that there have to be PeV protons accelerated in this source. So that will really be the first time that we can point to an extragalactic source accelerating high energy protons and producing high energy neutrinos. And the second source candidate was detected in an optical follow-up with the Zwicky Transient Facility. That's an optical survey instrument. And that's this tidal disruption event, AT2019 DSG. And if you, like me, have a hard time to remember those numbers, internally in ZTF, they call this Brent Stark, because they name all the TDE candidates after Game of Thrones characters. So this one is Brent Stark, and you see the optical light curve overlaid with the arrival of the neutrino. So the neutrino arrived roughly 150 days after the optical peak. First we thought, oh, this is pretty late. It's not what we had expected, but additional radio observations actually revealed that there was an inert engine active in the source that lasted actually much more than 100 days. So we actually confident that it's possible that this inner engine would still accelerate particles also at late times. So the neutrino association doesn't seem crazy. And also the chance coincidence to find a TDE brighter than this just by chance is 0.2%. So it's also roughly at 3 sigma level. So this is an interesting indication that maybe TDEs now can reveal as a new source class for high energy neutrinos. So if you take all this together, you can now ask yourself, like, how much would those different source classes contribute to the total diffuse neutrino flux? And this was done by Imre Bartosz and Marek Kowalski in this paper here, and they will take all the detections or candidates that have been identified and then conclude how much the source class can contribute. And they find that actually blazars are disfavored as the main source of high energy neutrinos, while other types of AGN can actually contribute significantly, up to 36%. And TDEs would contribute roughly 30%, and then there's still a third left for other source types that I cannot cover today. So yeah, it seems to be really just at the beginning of figuring out what could the high energy neutrino sources be, and that of course is connected to the sources of high energy cosmic rays. And over the next years, I think there will be interesting discoveries. So I'm quite excited about this, that the fact that we have a few candidates now, and now we can look at a larger population of sources. So in the last few minutes, I briefly want to talk about the third messenger that I haven't talked about so far, and those are gravitational waves. There have been several detections over the last year by LIGO and Virgo. Most of them were black hole mergers, but there was one really interesting one, the merger of 2 neutron stars. And this was a spectacular multi-messenger event. So on top of the gravitational wave signal, there was a gamma ray burst that was detected a bit more than a second after the gravitational wave signal, and then there was also optical, X-ray, and radio detection of this source. So what have we learned from all those observations? A lot. I just want to point out a few points. Before that, we were not sure how those gamma ray bursts would be produced. So it tells us that at least some of the short gamma ray bursts are produced by neutron star mergers. That was a model before, but now it's really confirmed. Then in the optical spectrum of the source, there were indications that the source contributes to production of heavier elements than iron, gold, for example. In addition to supernova explosions, those neutron star mergers can produce heavy elements. This event was used to probe Lorentz invariants, and there are some ideas how you could use this type of sources as an independent cosmological distance ladder. You can already do it with one source, but obviously the constraints you get are poor at this point. But if we find more of those sources with the electromagnetic counterpart, that would really be an independent measurement for the Hubble constant, for example. So that's quite exciting. Now, could we learn something if we find gravitational waves in coincidence with neutrinos? Yes, we can learn something because we believe we can learn something. IceCube, Antares, and Auger tried to find neutrinos in spatial and temporal coincidence with this neutron star merger in a plus minus 500 second time window. And you see the neutrinos detected in this time window here in the sky map, but the source in the end was localized to this part here. So none of the neutrinos that fell into the time window was in spatial coincidence, unfortunately. What was cool about this source was actually that so Auger can measure high energy neutrinos that are Earth skimming. This is where they are most sensitive. And by chance, this event was just in the region where Auger was sensitive, but unfortunately, no neutrinos were found. However, if we would find neutrinos in the future, and there are real-time searches for high energy neutrinos from gravitational wave events, then we could first constrain the direction of the event, because usually the gravitational wave events are huge bananas in the sky, And even though the neutrino resolution is not great, you can still like reduce the area to a much smaller region of the sky, and that would make it easier for other telescopes with a small field of view to follow up on that direction. And if we can establish that the neutrinos are emitted by those sources, then that would actually tell us something about the environment of the gravitational wave source, that it does produce high energy protons and they interact and produce high energy neutrinos. So we would really learn much more about the source itself. Yeah, in this search, nothing was found where we could set upper limits. This shows the sensitivity basically compared to the model predictions. So we were a bit unlucky in this case. First of all, the source produced a jet, but the jet was off axis, and you expect most of the neutrinos if the jet is on axis. That's the first part, and then it was in a not very favorable position of the sky, so also that reduced the sensitivity. So hopefully in the future, once observing run 4 starts, we find more of those events, and maybe we find also, for instance, neutrinos from those directions. So finally, yeah, I want to make the point that soon we will start run 4 for gravitational waves, adding also the Kagra detector. In the even more distant future, we will have LISA detecting gravitational waves in space. We have new neutrino detectors being constructed at the moment, and there's a huge amount of ground and space-based telescopes that will really be incredibly useful to do this combined searches for interesting multi-messenger events in the sky. So yeah, we're really just at the beginning. We have like one event with gravitational waves in an electromagnetic counterpart, and we have a few candidates for high energy neutrino sources with the counterpart. But yeah, I think there's exciting things to come in the future, and we should keep in mind that maybe we find something unexpected. Thanks.
Thank you, Anna. Thank you very much for this very nice and comprehensive talk. And also you are just in time. And we already have a question by Jorge Antonio Morales Soto. I read it to you. What about the new results from LASO about PEV gamma events? Are there relations to the sources you have searched for?
So they have this, I think, 12 PV events that they point out, or sources that they point out. One of them is the Crab Nebula, and I guess they believe that this is a leptonic source. The other ones, they have candidate sources in their paper, and some of them are pulsars or pulsar wind nebulas, or supernova remnants. And those would also be interesting, obviously interesting neutrino sources, and I'm sure there will be an analysis like looking for those positions in the sky with also with neutrinos to maybe find a correlation. So we have already done such a work with the Hawk data, but now of course this data is even closer in energy, so it's even more interesting.
Okay, thank you. There is another question from Slack this time. For a short gamma ray burst, how far off axis do you have to be before you can't see anything? What fraction of solid angle are we blind to?
So yeah, we can look at this plot here. So you really see in this model prediction, in this model, well, it all depends on the model, right? But if you look at this model, then yeah, you get most of the flux if you at 0 degrees. So this would be on axis, but then you see that you fall off quickly, right? At 8 degrees, you're always like 2 orders of magnitude below the flux you would expect to be on axis. But obviously, this is all dependent on the model, right?
As we have another 1 minute, I would like to ask about a little more about the prospects of the future KM3NET experiment. How can it contribute to, in particular, this multi-messenger astronomy with the gamma, the gravitational waves?
So yeah, I'm quite excited about the prospects for KM3NET, right? First of all, in combination with IceCube, it will then have a better coverage of the entire sky, because usually with the neutrino detectors, you are most sensitive to the opposite part of the sky. because you can use the Earth as a shield. So we really can cover then the entire sky. And another advantage in water is that you have a better angular resolution, which will help to really pinpoint the sources better, not suppress the background better. And then also you will, TAME3NET will have a better view on the galactic center, which will also be exciting.